Hey there and welcome. Today, we're going to learn a new language. Not Spanish, not French, but the language of chemistry. It's got its own vocabulary, its own grammar. And once you know the rules, you can literally write the recipe for everything in the universe.
So let's start with a question you've probably asked yourself at some point. We all know water is H2O, right? But why? Why is it always that exact recipe? Why isn't it H3O or maybe just HO? Is there some cosmic rule that says two hydrogens have to bond with one oxygen?
Well, it turns out there is. It's not random at all. It follows a super strict set of rules like grammar. Learning to write a chemical formula is just like learning to build a sentence. You just have to know the letters, the words, and the rules that connect them all together.
To really get these rules, we first have to understand the why. Why do atoms even bother combining in the first place? And the answer is actually pretty simple. They are all on a quest for one thing: stability.
You can almost think of atoms as being a little bit needy. They're in this constant struggle, as the quote says, to feel complete, to feel stable. And for most of them, that happy place, that feeling of being complete, means having a full outer shell of electrons.
And this stable state has a cool name, the octet state. Octa, as an octopus, means 8. Think of it like this. Imagine you're grabbing a handful of chocolates from a bowl. Your goal is to grab as many as your hand can possibly hold, right? Well, an atom is kind of the same. It wants to hold the maximum number of electrons its outer shell can handle, which is usually 8. That's when it's most balanced and stable.
And here is the key to, well, all of chemistry. This one single desire, to get a full outer shell, is what drives everything. Atoms will do whatever it takes. They'll give an electron away, they'll snatch one from a neighbor, or they'll even agree to share. And that very action, that giving, taking, or sharing of electrons, that's a chemical reaction. It's that simple.
Okay, so if getting that full octet state is the goal, how do atoms know how many electrons they need to trade? This is where our chemical grammar book comes in with a really important concept called valency. So what is valency? In simple terms, it's an element's combining power. It's just a number, and that number tells you exactly how many electrons an atom needs to gain, lose, or share to get stable. It's probably the most important rule in our entire chemical grammar book.
And this table shows it perfectly. Take a look at sodium. It's got just one lonely electron in its outer shell. Now, what's easier, trying to find and gain 7 more electrons, or just letting that one go? It's way easier to lose the one. So its valency is 1. Now look at chlorine. It has 7. It's so close to a full set of 8, it just needs to gain 1 more. So its valency is also 1. You see, it's all about finding the easiest, most efficient path to that stable state.
Now, something really important happens when an atom gives or takes an electron. It isn't electrically neutral anymore. It gets a positive or negative charge. These charged atoms are called ions or radicals. And these are basically the words we're going to use to build our chemical sentences. And there are 2 main types of these ions. If an atom gains electrons, it becomes an anion. Now, since electrons are negative, gaining them gives the atom a negative charge. Here's a little trick. Anion has an N in it, just like the word negative. On the other side, if an atom loses electrons, it becomes a cation. By losing negative charges, it's left with more positive protons, so it gets a positive charge. Just to make things a little more interesting, some elements can be a bit flexible. Take iron, for example. It can be stable after losing 2 electrons, or it can lose 3. So how do we tell them apart? We use a special naming rule. The version with the lower charge ends in us, so we call it ferrous. The one with the higher charge ends in ike, making it ferric. All right, let's recap. We have our goal, stability. We have our rules, valency. And we have our words, the ions. Now it's finally time to put it all together and actually write some chemical sentences. And we're going to do it with a really simple, almost foolproof tool called the crisscross method. So let's build something together. How about aluminum hydroxide? First step, we just have to identify our 2 parts. We have the aluminum ion, which has a charge of 3+, and we have the hydroxide ion, which is a little group of atoms with a charge of 1-. Okay, now for the method itself. It's just 4 easy steps. 1. Write the symbols down side by side, Al and OH. 2. Write their valency numbers, just the numbers, up above them, 3 and 1. 3, and this is super important, totally ignore the plus and minus signs for now. We only care about the numbers. And finally, step 4.
crisscross. The 3 that was with aluminum crosses down to hydroxide, and the 1 from hydroxide crosses down to aluminum.
And voila, here's our result. The 1 comes down next to the Al, and the 3 comes down next to the OH. Now, there are 2 little cleanup rules. First, in chemistry, we never write the number 1 as a subscript. It's just invisible. Second, because hydroxide, the OH, is a group of atoms, we have to put it in parentheses to show that the little 3 applies to the whole group. And there you have it, aluminum hydroxide is AlOH3. See? Not so bad.
Okay, you've got the basics down. Let's try one more. This one introduces one last, really important rule. How would we write the formula for calcium oxide?
All right, so calcium has a valency of 2, and the oxide ion also has a valency of 2. Now, if we just did the crisscross method, we'd get Ca2O2. But wait, here's the final rule. If the valency numbers are the same, or if they can be reduced to a simpler ratio, you have to simplify them. Chemical formulas are always written in the simplest whole number ratio. So the two 2's basically cancel each other out, leaving us with the correct, simplified formula, CaO.
And honestly, just like that, you've learned the fundamental grammar of chemistry. It's pretty cool, right? You now know why atoms react, you know what valency means, and you know how to use the crisscross method to put them together into compounds. You can officially read and write the language of matter.
You really do have the toolkit now to look at the world around you, from the salt on your food to the water in your glass, and understand how it's built on a chemical level. You know the rules of the language. So the only question left is, what will you build?